All right, so our next speaker needs no introduction. All right. No, it's my pleasure to introduce our next speaker, Michael, who has been kind enough to welcome me and many of my students over the years to the subject of difference equations, and it's a great pleasure as always to be here. So.
Thank you, Steve. So it's a pleasure to be here, so I'd like to thank all of you for coming here and supporting my sessions all these years and keeping the sessions very diverse. So I only have 20 minutes, so we're going to discuss dynamics of a discrete population model for extinction and sustainability in ancient civilizations. So this has been an ongoing project. I've been working together with my colleagues Bernie Brooks, Tomasz Wiant, and Bill Basner from Rochester Institute of Technology. Also, I'm only going to be speaking about extinction. My colleague Harold Hastings will be speaking to us about extinction and survival, which we've been recently working on, and then also other extensions been working on migration as well. So there's been many other projects I've been working together that started from this. Okay, so what led into this? The standard logistics model, growth rate, then the Basner-Ross model, invasive species model, and then of course what kind of long-term behavior. So these were the first three that were the motivations, and then these were the type of results that we had. And then also we're going to discuss continuous versus discrete. First of all, we're going to see not only a difference in the long-term behavior, also the transient behavior, but when do we consider continuous and when do we consider discrete when we're doing modeling. And we're going to see that's quite a vital question to address, because when you discretize a system, that is not going to give you the same results in a lot of the situations. Okay, so logistics model started as a standard way of modeling a lot of the population growth. So this is what we consider the standard logistics model, where we have C is the growth rate and capital K is going to be the carrying capacity. So my colleagues Bill Basner and David Ross started to study this over a decade ago. They were the pioneers of this project. So they were modeling extinction of population in Easter Island. So they were only considering the population of people. So dPdt is a growth rate of people, and the RDT the growth rate of the resources. So they only had two parameters, people and resources. That's how the model started with. So A is a growth rate of humans, and C is a growth rate of the resources, and H is going to be the harvesting rate. So those are the three vital factors that we need to consider when we consider population versus resources. And of course there's in reality a limit on how much you can use up the resources before they start to deplete very quickly. And in a lot of other ancient civilizations like the Vikings and the ancient Egyptians, the Mayas, the Incas, they all face the same dilemma. What is the limit, and how far can we really go past the limit before substantial problems or catastrophes start to happen. That was the original model. Then we decided to add invasive species, and it wasn't our idea. Our colleagues Terry Hunt from University of Hawaii, who's an anthropologist, and then Carl Lipo from California State University, who's also an anthropologist, said, well, the rats accelerated the rate of extinction. So they believed that they would have went extinct anyway, but because the Polynesians brought the rats to Easter Island, they believed that it accelerated the extinction rate. So they said, okay guys, let's try it and see what happens. So this is where my colleagues Bill Basner, Tomasz Wiant, and Bernie Brooks we started to investigate. So this time we rearranged things a little bit. So R now are going to be rats, and capital T are going to be the trees, because trees were the only resources that were available. So the rats in reality ate the seeds of the trees, and the trees did not reproduce. It really impeded the growth rate of the trees, and that's what Terry Hunt and Carl Lipo believed was the reason that it substantially accelerated the extinction rates of Easter Island. And of course, there are many other invasive species model, a lot of you have probably seen, but that's how really we started to change the model. So when we started this system of 3 equations nodes, so people, rats, and the trees, and also it's not only invasive species model, it's also a competitive model because trees and so rats and the humans are competing for trees. But of course the rats are going to win because their growth rate substantially dominates the human growth rate. So, and that's why our anthropology colleagues believe that that really accelerated the rate of extinction. So we did do a little bit of linear stability analysis, which I'm briefly going to breeze through. But generally the way we started analyzing the model was through a lot of the computations. So we had to pick different values of the parameters to get our hands wet. So I'm going to skip through these. So let me take the opportunity to show you some figures that happened. So F, the parameter, we chose these values, and we see for some values extinction happens very, very quickly, or you have survival happening. And so these are the Jacobian matrices, so we're going to breeze through. Now what is this? So this is the stability curve. So if we're going above this curve, then you're going to have one bifurcation, and you have below the curve you have a different bifurcation. So this is where they split off, so it's a hyperbola of where these bifurcations happened. But then we decided to discretize the model. That of course is a little different because you need to have, when you discretize, so population at year n+1 has to be population of at the previous year plus this. So this is where we still get the logistic rate, but you see you did not have this component and this component when you had the continuous. As you see here, this is continuous, this is discrete, and because of these extra terms here, we're going to see just catastrophic difference in the long-term behavior. We're going to get different stability diagrams, we're going to get different bifurcations. Now the question is, why go discrete? Well, in Antonio's model that he presented, of course he had very, very, if I'm not mistaken, compact population space where the next neighbor could be like a couple of centimeters away from you. Here on Easter Island, the next neighbor could be half a kilometer away from you, so it doesn't really make sense to have a continuous model when you have very sparse population. So if you're modeling big cities like Moscow, New York, or Tokyo, of course, neighbors are very close, but if you're living in the rural areas where the next neighbor could be a kilometer away from you, then there's much less interaction happening. That's one of the reasons we decided to to do discrete, because it made more sense. So here are some of the values we chosen, and what happens, the population growth, and then boom, collapse happens very, very quickly because because you use up the resources, and of course everything is good, but the moment the resources start depleting, then of course the survival rate really starts to diminish. And so here are the equilibria of the system, so I'm going to breeze through because we don't have too much time with this. However, what I do want to focus is this stability diagram. So based on all of these equations that you see here, we have determinants and the trace. So, and also with the discrete model, we have more tools to work on. We have determinants, a trace. For in the continuous, you have much less tools to work on. So we see that we have a much better decomposition. Instead of having just a hyperbola of what happens, now we have a triangle of what happens. So in fact, when we're on the horizontal line of the triangle, we're going to get Riemann-Sacker bifurcation happening. When we're on the diagonal line with a negative slope, we have flip bifurcation happening. And then when we're a diagonal line with a positive slope, we have a fold bifurcation happening. And you could see the horizontal axis is going to be the trace, and the vertical axis was the determinant. So thanks to discretizing, we see that we're able to have much better control of decomposing in regions where this one behavior happened versus the other. So we see that quite a big difference happens in not only different bifurcations. We have 3 different bifurcations, but we have a triangle of stability, so we have a much better grasp on our fingers with what indeed is happening as we're doing this. And again, because if you look back in the equations, you have this, and now you're adding an extra term, so we see that does make a difference for that reason alone. And of course, we had much better relationships when we had determinants and the trace, so we were able to get much better control on what was happening as we're doing this. And then we broke up into more additional regions. So we started with a stability triangle, and then based on these computations, we see that depending on the different values of A's, we have different slopes of the lines, and then also we see that depending on the values of A's and depending on the slopes, so for example, here they only intersect at 0, and then we have very nice decomposition where we have a fold bifurcation, stability, Riemann-Sachar bifurcation, but then when we increase the value of A, then you see lines start intersecting at other places besides 0, and that does complicate things a bit. So when you increase the population growth rate, you see that now you have a horizontal line happening. This line intersects this line where that did not happen in this case. So we see that starts to, that's why it's essential to keep the population rate low, so you don't end up with regions like this that are very difficult to analyze. So for example, if you look back at Steve's diagram where we had region 1 and region 3, so here we can have very nice decomposition here, but how do you analyze what happens in this region versus this region versus this region? That we did not investigate at all. So it's very similar, I believe, what happened in your situation, Steve, and it all depends on the value of A. As it gets closer and closer to 1, we see that we have less control on how do we decompose these regions as we're doing this. So let's discuss the Riemann-Sachar bifurcation. So analytically, these are the conditions on the relationship between the lines that permit this bifurcation to happen. So we choose different values of A's and C and H. So we see that we have transition. We have under 1 we have this, under 1 we have this, under 1 we have this. So in reality, you should have very strong sensitivity to initial conditions, and that does verify that based on the initial conditions and values of the parameters, both have to influence the long-term behavior, where the continuous model did not really have such strong sensitivity to initial condition as discrete one has. So let's take a look at some more. Again, if you recall this diagram that we had with these lines, so under one circumstance you have this, under one circumstance you have this, and under one circumstance you have this happening. So we see much more diversity of behavior that really should. Then of course we change things around a little bit, we do more iterations. We start to see a really big difference in not only in the long-term behavior, but within a particular group of behavior, we have different diagram happening. So we can really decompose, okay, under this circumstance we have this, and then within that we can decompose into more groups, so we gain much stronger grasp on what indeed is happening. And again, take a look at the difference between this, and this happening, all because we're changing the initial conditions and the values of A, so we have extremely strong sensitivity. So we have to be extremely careful what values of the parameters we change initial conditions. So as you can see, it's a much more sensitive system, yet it permits us to have much more control what's happening, where in the continuous we could not really have such very clear decompositions that are happening. And again, take a look at what is happening here, what is happening here, and what is happening here, all because we're just slightly changing different parameters of harvesting. So we see that the harvesting rate really makes a strong impact on what is happening. And in reality, of course, how we harvest does, if we over-harvest in reality, we know the consequences that could cause, and we can see here that does indeed confirm that we got to be very careful with not to over-harvest things. And again, take a look at, just change a few values of the parameters around, look at the difference between this, and this. I mean, this looks a little bit like this and this, but how do we possibly get this? So we see quite a lot of sensitivity is happening. It all depends on, because when we change the parameters, what kind of slopes of these lines So you see the slopes of these lines influenced, for example, slope is this, we get this. This slope gives us this. So again, we can just match like pieces of the puzzle which particular slope produces a particular diagram in these situations. And again, we have different scattered plots as we're doing this. So this has been going on for almost a decade. So we've written about 3 papers as we started the invasive species model. So first we had a continuous, then it was a discrete. And then I'm going to share what other ideas we've decided to have more accuracy of the model happening. Again, take a look at these diagrams. Then, again, we need to create more regions, so we decided to decompose into different, not only lines, but also subintervals. So, for example, if you're in a particular region, what kind of a particular Julia set do you produce? So we had to carefully decompose not only into regions, but intervals. So we decided to create these sets. And depending which particular subset of one of these sets, then you're going to get a particular diagram. So now instead of just slopes of lines, so we added, okay, so now we have these hyperbolas and lines put together. So what happens when you're in this region? What happens when you're in this particular region? What happens when you're in this particular region? So it becomes more confusing, but still we have more or less, yeah, thanks. When we start to introduce these other regions, all of a sudden the Julia set comes into the picture. So we really start to see more light at the end of the tunnel and the pieces of the puzzles matching more and more. So again, change the values of these parameters. So of course rats reproduce at a much higher rate than humans. That's why C is more than 3 times bigger than A. And again, you can see different Julia sets that we get depending on the harvesting rate. So the harvesting rate really causes a substantial impact on what kind of diagrams do we produce. Then it was Bernie Brooks' idea and invention to do diffusion, because he started that idea. So I'm going to use the board to introduce what is diffusion. So diffusion, so on Easter Island, so it's an island going around, so you can break up into these cells. So you have one neighbor, next neighbor here, next neighbor. So of course, let's call it N1 and N2, N3, and call it NK. So N1 has to interact with N2 regardless, you see, half a kilometer away or a kilometer away, and also with NK. So that's where we decided to do a diffusion model. So we had a paper on the diffusion model together with these, and that requires decoupling. That's where these come from. And then we had oscillatory behavior happening because the system that we had complex eigenvalues. That's why you see oscillatory behavior happening, and we see that sometimes if extinction happens, they descend. If not, they do not descend. So that also produced different ideas as we're doing this. Since I only have a very meager amount of time, so lately we've been working on 2 projects. Harold Hastings, right after me, will share with us extinction and survival. He's going to discuss, so if you're getting closer and closer to 0, how much more risk does that involve with the extinctions versus survival. So all of this work only dealt with extinction, did not deal with survival. Those are the 2 vital factors we need to look at. And we've been working on a project together with Carl Lipo and Terry Hunt on migration between the islands. So instead of looking at 2 neighbors on the island, look at neighboring islands. You have a whole cluster of islands, Polynesian islands, that could be quite close to each other. So what is a push-pull factor? So those are the things we're discussing that are all based on this. So this was a solid base of a lot of new ideas, and of course, not only for Easter Island, also for Vikings, for Aztecs, for Incas, all of these civilizations that went extinct over time because of over-harvesting or abuse of our resources. Okay, so I think we can probably stop here.
Any questions for our speaker? So I have one question.
Sure.
So you were looking at the extreme sensitivity on the initial conditions.
Mm-hmm.
What if I draw the initial conditions from, say, some nice distribution, and the values are constantly being updated? So it's not fixed at a given value, but it's drawn continuously over time from some nice distribution.
That's a very good question. We did not consider, we never thought of considering it here, but Harold, if I'm not mistaken, we are considering such factors in our new project.
Well, I guess really, to be very simple about it, that you probably don't, populations probably don't really exist for long in areas where there's extreme sensitivity. I mean, it's a little like your sampling stuff, right?
Right.
And you're going to see, if you sample, you're going to see populations that have survived more likely. A little like when you had your sequences of heads and tails. If I pick, for example, an H at random, it's probably from a longer sequence than a shorter sequence. Just, you know, your likelihood of picking a sequence. I'm actually going to be looking at trying to get a sense where things are not particularly sensitive. I think you're going to be away from these points, although they are of major interest. And part of the question is, can you detect flipping? I mean, this seems to be really a challenge.
Right.
Could you learn early on that you're in trouble? In some cases, this is a non-answer, I'm sorry.
No.
In some cases the answer is yes, in some the answer is
right.
no. Unfortunately, at times the answer is no. And the interesting thing that I'll mention briefly, it's really entirely work of others that I've just barely looked at. People have been sort of mystified in more recent collapses by non-return, say, of fisheries after they've sharply cut down the fisheries. And there may be some question of multiple steady states coming in these, so you drive it to some other steady state. And there's also a sense that where you have sensitive dependence, which maybe you do, you want to try to operate yourself outside of that parameter range. So you take this as a warning.
Right.
I think as Mike said, this is where it's very sensitive. You try to operate back here.
Yes.
So if I'm not mistaken, I think that's normalizing the model to sort of escape or reduce the problem with very strong sensitivity.
Or just saying that, for example, if you have some idea, if you could sort of calculate that a bifurcation is somewhere, and you're trying to control things, could you stay away from it? That's one of the questions.
Well, I think decomposing into regions, as we had, let me show you, okay, so when we had these region decompositions, probably you can just label them the colors where you have like the red is a warning, you don't want to be in this region, so we had, so let me go back to the slides here. Oh, okay, right here. So we can label colors. Okay, so this warning, this region, that's where you have extreme sensitive. So I guess you can probably investigate. So in this region, how much is sensitivity? In this region, how much? I guess. So we didn't investigate such very laconic details, but I imagine this region must have more strong sensitivity than this region. So the question is, it closer to zero or away from zero, or which one is going to be more sensitive to initial conditions?
Why don't you go back to the graph of the oscillations?
Sure.
Because that's really...
talking about these?
No. Just keep going. The earliest one is fine. The very early, with the F values, the series of F values in the collapse. It's right in the beginning. I think that's... Just keep all the way back.
All the way back?
Yeah. Right there.
These?
Yeah. So, I mean, the interesting challenge would be that if you look at the curve with the next to highest F, the bottom of those, there's damped oscillations that are slowly going.
Oh, the damped,
right?
I see.
So, I mean, the two changes with that. One is that the size of your steady states drop. The other is that you have increasing oscillations. And if you come back to Steve's suggestion, you could imagine this driven by noise. So
Right.
you're changing the conditions, not necessarily the initial conditions, but constantly there. And so, in some sense, if you were up near the top, this is just a guess, if you added random noise and you were near the top graph there, you'd see a very small amount of jitter about the steady state, because everything's damped out really fast. If you come down, you'll see a larger amount of jitter for the same amount of noise, because things are damped out much more slowly. Right? I mean, that just...
Okay.
And so, in fact, then if you see an increased amount of jitter, that might be, and I warn might be, a warning sign that you're operating nearer to a region of collapse. And then if you look at the last two curves, they don't look all that different for a while. I mean, that's the scary part for all of us in modeling. The last two, that they kind of like this, and then suddenly, that has been pointed out by a number of people that we may really want to begin to go to difference inequalities to do this, to bound ourselves strictly away from these bad scenarios.
Well, actually, I'd like to, how are we doing with time? Okay, we got a couple more minutes. Well, first of all, the reason that you have this happening, because if you recall the logistic difference equation, when you crank up this parameter higher than 3 or close to 4, then it really destabilizes. That's when you have a lot of these bifurcations happening. Like in fact, it's used in cardiology models, so logistic difference equation is a very, very essential component on this. Personally, I believe because of the logistic component, it creates these bifurcation, because itself that creates a lot of these. So I believe personally, due to the logistic equation again, that you have a lot of this phenomena happening. Because by itself, I mean, it creates, and then of course in the system, and it's trying to dominate the whole system, and that does dominate quite a bit, as we can see throughout the computations.
Right, let's thank our speaker again.
Okay, so our next speaker will